The topic for today is how to change variables. So we're talking about substitutions in differential equations, or changing variables. That might seem like a sort of fussy thing to talk about in the third or fourth lecture, but it isn't. The reason is that so far you know how to solve two kinds of differential equations, two kinds of first-order differential equations. The one where you can separate variables, and the linear equation that we talked about last time. Now, the sad fact is that in some sense those are the only two general methods there are. That those are the only two kinds of equations that can always be solved. Well, what about all the others? The answer is that to a great extent all the other equations that can be solved, the solution is done by changing the variables in the equation to reduce it to one of the cases that we can already do. Now, I'm going to give you two examples of that, two significant examples of that today, but ultimately, as you'll see, the way the equations are solved is by changing them into a linear equation or an equation where the variables are separable. However, that's for a few minutes. The first change of variables that I want to talk about is an almost trivial one, but it's the most common kind there is, and you've already had it in physics class. But I think it's so important in the science and engineering subjects that it's a good idea, even in 1803, to call attention to it explicitly. So in that sense, the most common change of variables is the one simple one called scaling. So again, the kind of equation I'm talking about is a general first-order equation. And scaling simply means to change the coordinates, in effect to change the axes, to change the coordinates on the axes, to scale the axes, to either stretch them or contract them. So what does the change of variable actually look like? Well, it means you introduce new variables where x1 is equal to x times something or times a constant. I'll write it as divided by a constant, since that tends to be a little bit more the way people think of it. And y the same. So the new variable y1 is related to the old one by an equation of that form. So a, b constants. So those are the equations. Now, why does one do this? Well, there are a lot of reasons, but maybe we could list them. For example, could be changing units. That's a common reason in physics. Changing the units that are used, you'd have to make a change of coordinates of this form. Perhaps an even more important reason is to, sometimes it's used to make the variables dimensionless. In other words, where so that the variables become pure numbers with no units attached to them. Since you're well aware of the tortures involved in dealing with units in physics, the point of making variables dimensionless, I don't have to sell that. Dimensionless, i.e., no units, without units. Without any units attached. It represents the number 3, not 3 seconds or 3 grams or anything like that. And the third reason is to reduce or simplify the constants. Reduce the number or simplify the constants in the equation. Reduce their number is self-explanatory. Simplify means make them less, either dimensionless also, or if you can't do that, at least less dependent upon the critical units than the old ones were. Let me give you a very simple example which will illustrate most of these things. It's the equation, it's a version of the cooling law which applies at very high temperatures, and it runs, so it's like Newton's cooling laws, except it's the internal and external temperatures are very, what's important is not the first power as in Newton's law, but the fourth power. So it's a constant, and the difference is now it's the external temperature, which just, so there won't be so many capital T's in the equation, I'm going to call M, to the fourth power minus T to the fourth power. So T is the internal temperature, the thing we're interested in, and M is the external constant, which I'll assume now is a constant external temperature. So this is for valid if a big temperature differences, Newton's law breaks down and one needs a different one. Now, you're free to solve that equation just as it stands if you can. There are difficulties connected with it because you're dealing with fourth powers, of course. But before you do that, one should scale. How shall I scale? Well, I'm going to scale by relating T to M. So the new variable I'm going to use is T1 equals T divided by M. This is now dimensionless because M, of course, has the units of temperature, degrees Celsius, degrees absolute, whatever it is, as does T, and therefore by taking the ratio of the two, it now becomes, there are no units attached to it. So this is dimensionless. Now, how actually do I change the variable in the equation? Watch this. It's an utterly trivial idea and utterly important. Don't slog around doing it this way, trying to stuff it in and divide first. Instead, do the inverse. In other words, write it instead as T equals MT1. The reason being that it's T that's facing you in that equation, and therefore T that you want to substitute for. So let's do it. The new equation will be what? Well, dt, since this is a constant, the left-hand side becomes dt1 dt times m equals k times m to the fourth minus m to the fourth t1 to the fourth. So I'm going to factor out that m to the fourth and make it 1 minus t1 to the fourth. Okay? Now, I can divide through by m and get rid of one of those. And so the new equation now is dt1 dt, the time, is equal to, now I have km cubed out front here. I'm going to just give that a new name, k1. Essentially, it's the same equation. It's no harder to solve nor and no easier to solve than the original one, but it's been simplified slightly. For one thing, it looks better. It looks better. Let's to compare the two, I'll put this one up in green and this one in green too, just to convince you it's the same, indicate that it's the same equation. Notice, so T1 has been rendered, is now dimensionless, so I don't have to even ask when I solve this equation, oh, please tell me what the units of temperature are. What kind of, how are you measuring temperature? It makes no difference to this equation. K1 still has units. What units does it have? It's been simplified because it now has the units of, since this is dimensionless and this is dimensionless, it has the units of inverse time. So K1, whereas it had units involving both degrees and seconds before, now it's inverse time as its units. And moreover, there's one less constant, so one less constant in the equation. It just looks better, in short. This business, I think you know that K1, the process of forming K1 out of K1 out of Km cubed is called lumping constants. I think they use that standard terminology in physics and in engineering courses. You try to get all the constants together like this, and then you lump them. They are lumped for you, and then you just give the lump a new name. So that's an example of scaling. Watch out for when you can use it. For example, it would have probably been a good thing to use in the first problem set when you were handling this problem of drug elimination and hormone elimination and production inside of the thing. You could lump constants, as was done to some extent on the solutions, to get a neater looking answer, one without so many constants in it. Okay, now let's now go to serious stuff, where we're actually going to make changes of variables which we hope will render unsolvable equations suddenly solvable. Now, I'm going to do that by making substitutions, but it's, I think, quite important to watch out that there are two kinds of substitutions. There are direct substitutions. That's where you introduce a new variable. I don't know how to write this on the board. I'll just write it schematically. So the new, it's one which says that the new variable is equal to some combination of the old variables. The other kind of substitution is inverse. It's just the reverse. Here you say that the old variables are some combination of the new. Now, often you'll have to stick in a few old variables too, but the basic, it's what appears on the left-hand side. Is it a new variable that appears on the left-hand side by itself, or is it the old variable that appears on the left-hand side? Now, right here we have an example. If I did it as a direct substitution, I would have written T1 equals T over M. That's the way I define the new variable, which of course you have to do if you're introducing it. But when I actually did the substitution, I did the inverse substitution. Namely, I used T equals T1, M times T1. And the reason for doing that was because it was the capital T's that faced me in the equation, and I had to have something to replace them with. Now, you've seen this already in calculus, this distinction, but that might have been a year and a half ago. Just let me remind you. Typically in calculus, for example, when you want to do this kind of integral, let's say x times the square root of 1 minus x squared dx, the substitution you would use for that is u equals 1 minus x squared, right? And then you'd calculate, and then you'd observe that the x dx more or less makes up du apart from a constant factor. So this would be an example of direct substitution. You'd put it in and convert the integral into an integral in u. What would be an example of inverse substitution? Well, if I take away the x and ask you instead to do this integral, then you know that the right thing to do is not to start with u, but to start with the x and write x equals sine or cosine u. So this is a direct substitution in that integral, but this integral calls for an inverse substitution in order to be able to do it. And notice they look practically the same, but of course, as you know from your experience, they're not. They're very different. Okay, so I'm going to watch for that distinction as I do these examples. And the first one I want to do is an example of a direct substitution. So it applies to an equation of the form y prime equals, there are two kinds of terms on the right-hand side. A of x, let's use P of x. P of x times y plus q of x times any power whatsoever of y. Well, notice, for example, if n were 0, what kind of equation would this be? Y to the n would be 1, and this would be a linear equation, which you know how to solve. So n equals 0, we already know how to do, so let's assume that n is not 0, so that we're in new territory. Well, if n were equal to 1, you could separate variables, so that too is not exciting, but nonetheless, it will be included in what I'm going to say now. If n is 2 or 3, or n could be 1/2, so n anything. Even 0 is all right, it's just silly. Any number. Could be negative, n equals -5, that would be fine also. This kind of equation, to give it its name, is called the Bernouilli equation. Named after which Bernouilli, I have not the faintest idea. There were, I think, 3 or 4 of them, and they fought with each other, but they were all smart. Now, the key trick, if you like, method to solving any Bernoulli equation, let me call one other thing I should call out. Most important is what's missing. It must not have a pure x term in it. And that goes for a constant term either. In other words, it must look exactly like this. Everything multiplied by y, or a power of y, 2 terms. So, for example, if I add 1 to this, the equation becomes non-doable. Right? It's very easy to contaminate it into an equation that's unsolvable. It's got to look just like that. Now, you got one on your homework. So you got several. Both part 1 and part 2 have Bernoulli equations on them. So, you know, this is practical in some sense. What do we got? The idea is to divide by y to the n. Ignore all formulas that you're given. Just remember that when you see something that looks like this, or something that you can turn into something that looks like this, divide through by y to the nth power, no matter what n is. All right, so y prime over y to the n is equal to p of x times 1 over y to the n minus 1, right? Plus q of x. Well, that certainly doesn't look any better than what I started with, and in your terms it probably looks somewhat worse because it's got all those y's of the denominator, and who wants to see them there? But look at it. In this very slightly transformed Bernoulli equation is a linear equation struggling to be free. Where is it? Why is it trying to be a linear equation? Make a new variable. Call this hunk of it a new variable. Let's call it v. So v is equal to 1 over y to the n minus 1. Or if you like, you can think of that as y to the 1 minus n. What's v prime? So this is the direct substitution I'm going to use. But of course, the problem is, what am I going to use on this? Well, the little miracle happens. What's the derivative of this? It is 1 minus n times y to the negative n times y prime. In other words, up to this constant factor 1 minus n, it's exactly the left-hand side of the equation. Well, let's make n not equal 1 either. As I said, you can separate variables if n equals 1. What's the equation then turned into? Our Bernoulli equation divided through in this way is then turned into the equation 1 minus n, v prime divided by 1 minus n is equal to p of x times v plus q of x. It's linear. And now solve it as a linear equation. Solve it as a linear equation. You notice it's not in standard form, not in standard linear form. To do that, you're going to have to put the p on the other side. That's okay, that term on the other side. Solve it, and at the end, don't forget that you put in the v. It wasn't in the original problem, so you have to convert the problem back, the answer back in terms of y. It'll come out in terms of v, but you must put it back in terms of y. Let's do a really simple example just to illustrate the method and to illustrate the fact that I don't want you to memorize formulas. Learn methods, not final formulas. So suppose the equation is, let's say, y prime equals y over x minus y squared. That's a Bernouilli equation. I could, of course, have concealed it by writing xy prime plus xy prime minus xy equals negative y squared. Then it wouldn't look instantly like a Bernouilli equation. You'd have to stare at it a while and say, hey, that's a Bernouilli equation. Okay, but so I'm handing it to you on a silver platter, as it were. So what do? Divide through by y squared. So it's y prime over y squared equals 1 over x times 1 over y minus 1. And now the substitution that I'm going to make is for this thing. V equals 1 over y. It's a direct substitution. V prime is going to be negative 1 over y squared times y prime. Don't forget to use the chain rule when you differentiate with respect, because the differentiation is with respect to x, of course, not with respect to y. Okay, so what's this thing? That's the left-hand side. The only thing it's got a negative sign. So this is minus v prime equals 1 over x stays 1 over x, 1 over y. So it's v over x minus 1. So let's put that in standard form. In standard form, it will look like, first imagine multiplying it through by negative 1 and then putting this term on the other side, and it will turn into v prime plus v over x is equal to 1. So that's the linear equation in standard linear form that we're asked to solve, and the solution isn't very hard. The integrating factor is, well, I integrate 1 over x, that makes log x, and e to the log x, so is e to the log x, which is, of course, just x itself. So I should multiply this through by x to be able to integrate it. Now, some of you, I would hope, just can see that right away, that if you multiply this through by x, it's going to look good. So after we do multiply through by x, what do I get? X v prime for the, maybe I shouldn't skip a step. You're still learning this stuff, so let's not skip a step. So it becomes xv prime plus v equals x, okay? After I multiplied through by the integrating factor, this now says this is xv prime, and I quickly check that that in fact is what it's equal to, equals x, and therefore xv is equal to 1/2 x squared plus a constant. And therefore v is equal to 1/2 x plus c over x. You can leave it in that form, or you can combine terms. It doesn't matter much. Am I done? The answer is no, I am not done, because nobody reading this answer would know what v was. V wasn't in the original problem. It was y that was in the original problem, and therefore I have to, the relation is one is the reciprocal of the other, and therefore I have to turn this expression upside down. Well, if you're going to have to turn it upside down, you probably should make it look a little better. Let's rewrite it as x squared plus 2c, combining fractions, I think they call it in high school or elementary school, plus 2c. How's that? X squared plus 2c divided by 2x. Now 2c, you don't call a constant 2c because it's just as arbitrary to call it c1. So I'll call that, so my answer will be y equals 2x divided by x squared plus an arbitrary constant. But to indicate it's different from that one, I'll call it c1. c1 is 2 times the old one, but that doesn't really matter. So there's the solution. It has an arbitrary constant in it, but you notice not an additive arbitrary constant. The arbitrary constant is tucked into the solution. If you have to satisfy an initial condition, you would take this form and starting from this form, figure out what C1 was in order to satisfy that initial condition. Thus, Bernoulli equation is solved. Our first Bernoulli equation. Isn't that exciting? Here was the equation, and there is its solution. Now, the one I'm asking you to solve on the problem set in part 2 is no harder than this, except I ask you some hard questions about it. Not very hard, but a little hard about it. But I hope you'll find them interesting questions. You already have the experimental evidence from the first problem set, and the problem is to explain the experimental evidence by actually solving the equation and seeing. I think you'll find it interesting, but maybe that's just a pious hope. Okay. I'd like now to turn to the second method, where a second class of equations which require inverse substitution. And those are equations which are called homogeneous, a highly overworked word in differential equations and in mathematics in general, but it's unfortunately just the right word to describe them. So these are homogeneous first-order ODEs. Now, I already used the word in one context in talking about the linear equation when 0 was the right-hand side. This is different, but nonetheless, the two uses of the word have the same common source. A homogeneous differential equation, homogeneous newspeak, is y prime equals, it's a question of what the right-hand side looks like. And now the simplest way to say it is, you should be able to write the right-hand side as a function of a combined variable y divided by x. In other words, after fooling around with it, the right-hand side a little bit, you should be able to write it so that every time a variable appears, it's always in the combination y over x. Let me give some examples. For example, suppose y prime were, let's say, x squared y divided by x cubed plus y cubed. Well, that doesn't look in that form. Well, yes, it is. Imagine dividing the top and bottom by x cubed. What would you get? The top would be y over x, if you divided it by x cubed. And if I divide the bottom by x cubed also, which of course doesn't change the value of the fraction, as they say in elementary school, 1 plus y over x cubed. So this is the way it started out looking, but you said, aha, that was a homogeneous equation because I could see it could be written that way. How about another homogeneous equation? How about xy prime? Is that a homogeneous equation? Of course it is, otherwise why would I be talking about it? If you divide through by x, you can tuck it inside the radical, the square root, if you remember to square it when you do that. And it becomes the square root of x squared over x squared, which is 1, plus y squared over x squared. It's homogeneous. Now, you might say, hey, this looks like you have to be rather clever to figure out if an equation is homogeneous. Is there some other way? Yeah, there is another way. And it's the other way which explains why it's called homogeneous. You can think of it this way. It's an equation which is, in modern speak, invariant under the operation zoom. What is zoom? Zoom is you increase the scale equally on both axes. So the zoom operation is the one which sends x into a times x and y into a times y. In other words, you change the scale on the both axes by the same factor a. Now, what I say is, gee, maybe I shouldn't write it like this. Why don't we say we introduce, how about this? So think of it as a change of variables, like we'll write it like that. So you can put here an equal sign if you don't know what this meaningless arrow means. So I'm making this change of variables, and I'm describing it in the inverse as an inverse substitution. But of course, it wouldn't make any difference if it's exactly the same as the direct substitution I started out with. Under scaling, the only difference is I'm not using different scales on both axes. I'm expanding them both equally. That's what I mean by zoom. Now, what happens to the equation? Well, what happens to dy over dx? Well, dx is a dx1, dy is a dy1, and therefore the ratio dy by dx is the same as dy1 over dx1. So the left-hand side becomes dy1 over dx1, and the right-hand side becomes f of, well, y over x is the same as y over y. Since I've scaled them equally, this is the same as y1 over x1. So it's y1 over x1, and the net effect is I simply, everywhere I have an x, I change it to x1, and wherever I have a y, I change it to y1, which, what's in a name? It's the identical equation. So I haven't changed the equation at all by a zoom transformation, and that's what makes it homogeneous. That's not an uncommon use of the word homogeneous. It's, you know, when you say space is homogeneous in every direction, well, that means, I don't know, means it's this, you know, just saying, okay, that's, I'm getting into trouble there. I'll let it go with this since I can't prepare any better. I haven't prepared any better explanation, but this is a pretty good one. Okay, so suppose we've got a homogeneous equation. How do we solve it? So here's our equation, f of y over x. Well, what substitution would you like to make? Obviously, we should make a direct substitution, z equals y over x. So why did he say that this was going to be an example of inverse substitution? Because I wanted to confuse you. But look, that's fine. You will know, if you write it in that form, you will know exactly what to do with the right-hand side. And this is why everybody loves to do that. Unfortunately, you have to substitute into the left-hand side as well. And I can testify from many years of looking with sinking heart at examination papers, what happens if you try to make a direct substitution like this? You say, oh, I need z prime. Z prime equals, well, I better use the quotient rule for differentiating that. And, you know, it comes out this long, and then either a long pause, what do I do now? Because it's not at all obvious what to do at that point. Or, much worse, 2 pages of frantic calculations and giving up in total despair. Now, the reason for that is because you tried to do it making a direct substitution. All you have to do instead is treat it as an inverse substitution, write y equals zx. What's the motivation for doing that? It's clear from the equation. When you have to, and this goes through all of mathematics, whenever you have to change a variable, whenever you have to change, whenever you have to change a variable, look at what you have to substitute for and focus your attention on that. I need to know what y prime is. Okay, well then I better know what y is. If I know what y is, do I know what y prime is? Oh, of course. Y prime is z prime x plus z times the derivative of this factor, which is 1. And now I've turned, with that one stroke, the equation has now become z prime x plus z is equal to f of z. Well, I don't know. Can I solve that? Sure. Sure, that can be solved because this is x times dz dx. Just put the z on the other side. It's f of z minus z. And now this side is just a function of z. Separate variables. And the only thing to watch out for is at the end, the z was your business. You've got to put the answer back in terms of x and y. Okay, let's work an example of this. Since I haven't done any modeling yet this period, let's make a little model, differential equations model. In other words, a physical situation which will be solved by an equation, and guess what? The equation will turn out to be homogeneous. Okay. So the situation is as follows. We're in the Caribbean somewhere, a little isolated island with a lighthouse on it at the origin, and a beam of light shines from the lighthouse. The beam of light can rotate the way lighthouse beams, but this particular beam is being controlled by a guy in the lighthouse who can aim it wherever he wants. And the reason he's interested in aiming it wherever he wants is that there's a drug boat here, which has just been caught in the beam of light. So, drug boat. Which has just been caught in the beam of light and feels it's better escape. Now, the lighthouse keeper wants to keep the drug boat, the light shining on, so that the U.S. Coast Guard helicopters can zoom over it and do whatever they do to drug boats. I don't know. So the drug boat immediately has to follow an escape strategy, and the only one that occurs to him is to, well, he wants to go further away, of course, from the lighthouse. On the other hand, it doesn't seem sensible to do it in a straight line because the beam will keep shining on him. So he fixes the boat at some angle, let's say, and goes off so that the angle stays 45 degrees. So goes so that the angle between the beam and the draw the beam a little less like a 45-degree angle. So the angle between the beam and the boat's path is always 45 degrees. Goes at a constant 45-degree angle to the beam, hoping thereby to escape it. On the other hand, of course, the lighthouse guy keeps the beam always on the boat. So it's not clear it's a good strategy, but this is a differential equations class. The question is, what's the path of the boat? What's the boat's path? Now, an obvious question is, why is this a problem in differential equations at all? In other words, looking at this, you might scratch your head and try to think of different ways to solve it. But why? What suggests that it's going to be a problem in differential equations? The answer is, you're looking for a path. The answer is going to be a curve. A curve means a function. We're looking for an unknown function, in other words. And what type of information do we have about the function? The only information we have about the function is something about its slope. That its slope makes a constant 45-degree angle with the lighthouse beam. Its slope makes a constant angle, makes a known angle to a known angle. Well, if you're trying to find a function and all you know is something about its slope, that is a problem in differential equations. Well, let's try to solve it. Let's see. Well, let me draw just a little bit. So here's the horizontal. Let's introduce a coordinate system. In other words, there's a horizontal, and here's the boat to indicate where I am with respect to the picture. So here's the boat. Here is the beam. And the path of the boat is going to make a 45-degree angle with it. So this is the path that we're talking about. And now let's label what I know. Well, this angle is 45 degrees. This angle I don't know, but of course I can calculate it easily enough because it has to do with, if I know the coordinates of this point, xy, then of course that horizontal angle, I know the slope of this line, and that angle will be related to the slope. So let's call this alpha. And now what I want to know is what the slope of the whole path is. So y prime, so let's call y equals y of x, the unknown function, whose graph is going to be the boat's path. Unknown graph. What's its slope? Well, its slope is the tangent of the sum of these two angles, alpha plus 45 degrees. Now, what do I know? Well, I know that the tangent of alpha is how much? That's y over x. In other words, if this is the point x over y, this is the angle it makes with the horizontal. If you think of it over here, this is parallel. So this angle is the same as that one, and it's y over, its slope is, of that line is y over x. So the tangent of the angle is y over x. How about the tangent of 45 degrees? That's 1. And there's a formula. This is the hard part. All you have to know is the formula exists, and then you look it up if you've forgotten it, relating the tangent, giving you the tangent of the sum of two angles. And you can, if you like, clever, derive it from the formula for the sine of and cosine of the sum of two angles, but one peek is worth 1,000 finesses. So it is the tangent of alpha plus the tangent of 45 degrees, let me write it out in all its gory details, divided by 1, so you'll at least learn the formula, 1 minus tangent alpha times tangent 45 degrees. This would work for the tangent of the sum of any two angles. That's the formula. So how does that, what do I get then? Y prime is equal to the tangent of alpha, which is y over x, oh, I like that combination, plus 1 divided by 1 minus y over x times 1. Now, there's no reason for doing anything to it, but let's make it look a little prettier and thereby make it less obvious that it's a homogeneous equation. If I multiply top and bottom by x, it looks prettier. X plus y over x minus y equals y prime. That's our differential equation. But notice that last step to make it look pretty has undone the good work. It's fine if you immediately recognize this as being a homogeneous equation because you can divide top and bottom by x. But here it's a lot clearer that it's a homogeneous equation because it's already been written in the right form. Okay, let's solve it now since we know what to do. We're going to use as the new variable z equals y over x. And as I wrote up there, z for y prime will substitute z prime x plus z. And with that, let's solve. Let's solve it. The equation becomes z prime x plus z is equal to z plus 1 over 1 minus z. put the z on the other. We want to separate variables, so you have to put all the z's on one side. So this is going to be x dz dx equals this thing minus z, which is z plus 1 over 1 minus z, and now, as you realize, putting it on the other side, I'm going to have to turn it upside down. Just as before, if you have to turn something upside down, it's better to combine the terms and make it one tiny little fraction. Otherwise, you're in for quite a lot of mess if you don't do this nicely. So z plus 1 minus z, that gets rid of the z's. The numerator is 1 minus z squared over 1 minus z. I hope. 1, is that right? 1 plus z squared over 1 minus z. And so the equation is dz, and what is the, put this on the other side and turn it upside down, so that will be 1 minus z over 1 plus z squared on the left-hand side, and on the right-hand side, dx over x. Well, that's ready to be integrated just as it stands. The right-hand side integrates to be log x. The left-hand side is the sum of two terms. The integral of 1 over 1 plus z squared is the arctangent of z, maybe? The derivative of this is 1 over 1 plus z squared. How about the term z over 1 plus z squared? Well, that integrates to be a logarithm. It's more or less the logarithm of 1 plus z squared. How much do I, if I differentiate this, I get 1 over 1 plus z squared times 2z, but I wish I had negative z there instead. Therefore, I should put a minus sign, and I should multiply that by half to make it come out right. And this is log x on the right-hand side plus put in that arbitrary constant. And now what? Well, let's now fool around with it a little bit. The arctangent, I'm going to simultaneously, no, two steps. I have to remember your innocence, okay. Although probably a lot of you are better calculators than I am. I'm going to change this, use as many laws of logarithms as possible. I'm going to put this in the exponent and put this on the other side. That's going to turn it into the log of 1 plus z squared, the square root of 1 plus z squared. And this is going to be plus the log of x plus c. And now I'm going to go back and remember that z equals y over x. So this becomes the arctangent of y over x equals, now, I combine the logarithms. This is the log of x times this square root, right? Make one logarithm out of it. And then put z equals y over x. And you see that if you do that, it'll be the log of x times the square root of 1 plus y over x squared. And what is that? Well, if I put this over x squared and take it out, it cancels that. And what you're left with is the log of the square root of x squared plus y squared plus a constant. Now, technically, you've solved the equation, but not morally. Because, I mean, my God, what a mess, incredible path. Who could, tells me absolutely nothing. Wow, what is this screaming? Change me to polar coordinates. What's the arctangent of y over x? Theta in polar coordinates. It's theta. This is r. So the curve is theta equals the log of r plus a constant. And I can make even that look a little better if I exponentiate everything. Exponentiate both sides, combine this in the usual way, and what you get is that r is equal to some other constant times e to the theta. That's the curve. It's called an exponential spiral, and that's what our little boat goes in. And notice, probably if I'd set up the problem in polar coordinates from the beginning, nobody would have been able to solve it, but anyone who did would have gotten that answer immediately. Thanks.